I didn't bother to capture this and put it into notebook software, but I'm going to run through all of these items with you. During the photoelectric effect, just generally speaking, what happens is light is incident on a piece of metal. Incident on a piece of metal simply means the light is going to hit the metal, and electrons are ejected from the surface of the metal. It's not that important that you know they're ejected from the surface, but they don't tunnel their way through a big chunk of metal. They're the surface atoms that lose electrons. The photoelectric effect, the second point, says that it will not happen unless the frequency of the radiation incident on the metal has a minimum value. The frequency of the light has to be greater than some minimum value, and that minimum value is called the threshold frequency. I don't know how much I stressed this yesterday, but every metal has its own threshold frequency. A metal with a very low threshold frequency has electrons that are held very loosely to the atoms, whereas an electron that's held very strongly to an atom would be in a metal with a high threshold frequency. What the implication is here is that the photons that are striking the metal, I'm looking at the third point right now, the photons that are striking the metal must have a minimum amount of energy. And as soon as you understand that, I'm going to open up another file here while I'm talking. As soon as you understand that what's really going on is that the photon hitting the metal has to have a minimum amount of energy, then this whole process starts to make more sense. Because when we talk about energy, that explains everything that's going on with the photoelectric effect. The electron gets kicked out with energy because it was given energy to begin with. So when we say that the photons have to have a minimum frequency, or the light has to have a minimum frequency, we're really saying the photon energy has to be bigger than some minimum amount. That minimum photon energy that could be required for a particular metal is called the work function of the metal. And that translates into this picture on that handout I gave you yesterday. The fourth point is just telling you that when the photons strike the metal, there's a one-to-one interaction between each photon and each electron. And as soon as you understand that these little bundles of light energy are being absorbed one at a time by individual electrons. A single electron never absorbs 2 or 3 or 4 photons. A single electron only absorbs 1 photon. As soon as you understand that, then this makes sense. That if you increase the brightness of the light, then you get more electrons coming off of the surface of the metal, because brighter light has more photons. Side note here, in terms of experimentation, you don't measure the number of electrons coming off directly, you measure the electric current being created. But a greater current means more electrons. The fifth point on this new handout says that each electron needs a certain amount of energy to remove itself from the metal. This is at the top of the screen right now. And that requirement is called the work function. And it seems as though now, at least to me, we're kind of going in circles saying the same thing over and over again. That's why photons must have a minimum amount of energy. How do we get a photon with the minimum amount of energy? You have to have a minimum frequency, because the bigger the frequency, the bigger the energy. If the electron is given more than enough energy to leave the metal, why would the electron be given more than enough energy to leave the metal? Because the photon it absorbs has more energy than the work function. Then the electron will escape the bonds of the metal and be free. If the electron is not given enough energy to escape the metal, so why would an electron not be given enough energy? Because the photon it absorbs has less energy than the work function. Then the electron doesn't escape. If the electron does escape, then any energy that's left over is kinetic. And then the last 3 points are just really descriptions of procedures and pieces of information you need to know in the course of doing calculations. W is the symbol we give for the work function, and we can work in joules or eV. The threshold frequency is F sub 0. and it's in hertz. And the work function can be calculated by taking the threshold frequency times Planck's constant. So let's look at these additional examples one at a time. And I'm not going to write anything down here. I want to open this up in a different folder. I don't like Google Chrome for viewing these. So let me close out my Chrome. So we're just going to talk about these examples. And if you choose to write stuff down on this handout, you certainly can. I'm not going to be writing anything. In an experiment, when you shine green light on a metal, electrons are ejected. What does that tell you? It tells you that the green light has a frequency greater than the threshold frequency. What could you change if you wanted electrons to be ejected with more energy? So how could you repeat this experiment? I am going to write something down here. What could you change in this experiment to not change the number of electrons that come off, but instead to change the energy that each electron has? And there's two answers to this question. Farhad? Turns out no. Because if you change the brightness, all you will be doing is raining more photons down on the metal, but each of those photons will still only have the same energy they currently have, which means each electron, bear with me, which means each electron will be given the same amount of energy, which means each electron will get to keep the same amount of energy as the dimmer green light provided them. Right, so hit it with a smaller wavelength or a higher frequency. So one of the changes is use a higher frequency, or as you put it, Liam, a shorter wavelength. In other words, and I'm a little embarrassed to admit I always have to say Roy G. Biv and sort this out in my head. You have to use a color of light that is more energetic than green. Red won't do it. Incidentally, if you use red light, there's not even a guarantee the electrons will be ejected, because maybe red light is below the threshold frequency. So you need to be looking at blue, violets, UV, X-ray. I mean, we could say gamma as well, but that's maybe going overboard. Gamma, you might just obliterate the metal into pieces. There's another change you could make to this experiment, and I do believe there's value in us talking about these questions. I think you get a deeper understanding of the photoelectric effect. Does anybody know of another change we could make to this experimental design? Willis? Perfect. Use a metal with a lower threshold frequency or a lower work function. And the reasoning is this, and again, bear with me, it seems like what I'm going to say ends and then I continue to say more. In the case of the original experiment, each electron is given a certain amount of energy by those photons, by each photon, by one photon. And that electron has that amount of energy, and it's got to give up some of its energy that was given to it to get out of the metal, so it has something left over. And it will have more than enough. It will have something left over because you're told the electrons are ejected in the original experiment. When the green photons, which are still identical, hit the second metal, they still give each electron that amount of energy that they gave each electron in the first experiment. But this time, since the threshold frequency is less, which means the work function of the metal is less, the cost of electron freedom is less. So the electron was still given the same amount of energy, it just doesn't have to spend as much to get out, so it's going to have more left over, which means the electron will have more kinetic energy. Each electron will have more kinetic energy. Let's take a look at the next question. In an experiment, when green light is incident on a metal, photoelectrons are ejected. Okay. Same setup as the first question. If you wanted fewer electrons to be ejected, each with the same energy that they were ejected with before, what could we do to the experiment? Farhan. And could you be more specific? Because change the brightness can mean a number of things. Right. So, reduce the brightness. There's lots of ways to say that, by the way. I could say make the light dimmer. That would be a way of saying reduce the brightness. I could say reduce the intensity of the light. That's the same thing. And the reason, as Farhan was saying, is that if you have dimmer light or less bright light or weaker is maybe a word I would stay away from. You have dimmer light, that means you have fewer photons hitting the metal per second. There's still those green photons. So each electron still picks up that photon energy. Each electron still loses the work function. Each electron still keeps the same energy left over that it had before we reduced the brightness. But because there's fewer photons, there will be fewer electrons. By the way, in this case, what you would discover would be the electric current in the cell would decrease because you have fewer electrons. In question 1, what you would discover is that the stopping voltage would increase because each electron has more energy. Do questions 1 and 2 make sense to you? All right. You could certainly combine them. I could have asked you a question about, well, how can we get fewer electrons but each with more energy? That's a possibility too. But let's take a look at number 3. In an experiment, green light is incident on a metal. Boy, I'm really fixating on green light in all of these. This is number 3, but no photoelectrons are ejected. Well, that's different. So we shine the green light on, we look at the ammeter, nothing. No electrons are ejected. What would you expect to happen if you used red light instead of green light? Ben? Nothing. Is it a guarantee that nothing would happen? It is. Because red light has a lower frequency than green light. So, to put it into pictorial terms for you, if you take a look at these pictures of photons, this is just a model, and you take a look at how much energy a green photon has, it has a lot more energy than a red photon. Well, a lot. It has more energy than a red photon. So if the green photon does not have enough energy to cause electrons to escape, that means the green photon's energy is smaller than the work function, which would mean a red photon is even smaller than the work function. So you would expect no change to occur here. And you would be right. No change. No electrons ejected. What about if we increase the brightness of the green light? Evan? Right. No change. And this is where we have to kind of talk about particle models of light, because increasing the brightness of light means adding more light energy to the problem. But it doesn't matter how much energy you add in terms of more photons. It's a one photon, one electron interaction. And if that green photon has not enough energy to break the work function, To remove the electron, nothing happens. So again, no change. No electrons ejected. What about if we use a metal with a lower threshold frequency? Give everybody a second to think about that. We're going to use a metal with a lower threshold frequency. Farhan.
It all depends on how much lower the frequency is. If the frequency is low enough for green light to eject electrons, that's what would happen.
Perfect. It depends on what that threshold frequency is. If you take a look at the frequency of green light, if the frequency of the green light is greater than the threshold frequency of the metal, so you've gone to a very, very low threshold frequency. You've maybe used something like sodium, which has an incredibly small threshold frequency, then electrons will be ejected. But if the threshold frequency is less than, or if the frequency of green light is less than the new threshold frequency, so maybe you decrease the frequency, the threshold frequency of the metal, but you just decrease it to something that is still a bigger frequency than the frequency of green light. That's confusing. No electrons will be ejected. So it depends. What if we use blue light? Is it a guarantee the photoelectric effect is going to happen because we've increased the frequency? No. Could the photoelectric effect happen? Yes. It depends on where the threshold frequency is. And again, this is all about, for this question, this diagram, right? There's the green light. At the start of example 3, we are dealing with this situation where the threshold frequency is more than the frequency of green light. So green light does not have a sufficient energy in terms of photon energy. If you use blue light, well, blue light won't cause it according to this, but what if the threshold frequency when you started was here? And you use blue light, then the frequency of light used is more than the threshold frequency. So I'm not going to write that down. I think you get that. It's going to depend on the situation. The final few examples, actually we're not going to do number 5. Number 4, we have a threshold frequency of a metal of 5.8 times 10 to the 14 hertz. What I want everybody to do is calculate the work function in number 4. I'll write down minimal amount of stuff here. So I'm asking you to calculate the work function of this metal. And even though you may have started, it's not too late. I want it in electron volts. I think electron volts are easier to use in terms of learning and understanding what's going on. This is just using work equals HF0. That's the formula you use for the work function. There's no real shortcut here. You can't use the 1242 because that's a frequency, not a wavelength. So you take Planck's constant in EV nanometers and multiply by 5.8 times 10 to the 14 hertz. I believe I just said you take Planck's constant in EV nanometers. I think that came out of my mouth. What I meant to say was electron volt seconds. Times the frequency. Anybody else get 2.4012? So this is the work function in electron volts. 2.4012 EV. Will a 600 nanometer photon absorbed by an electron in this metal kick the electron out? Well, what you have to know is how much energy that photon is. I want you, wherever possible, thinking in terms of energy and not frequency or wavelength. So the quickest way to figure out what this energy is to take 1242 divided by 600, and you will get the energy in electron volts. And by my calculation, you get 2.06, I think. But I'm wrong. I could tell right away by the looks on your faces. What do you get? 2.07? Okay, that was close. You get 2.07 EV. While we're at it, why don't you calculate the electron volt energy of a 500 nanometer photon, which is what we're talking about in B. $1.484. So you get 2.484. 2.484 eV. So will this 600 nanometer photon eject an electron from the metal? No, because the energy is less than the work function. That was a bad idea for me to write it that way. I'm just going to say less than the work function, so no photoelectric effect. I know some of you would be curious as to what happens. And very often in this course somebody asks, so what happens then? The electron absorbs the energy and then it doesn't leave the metal. I would say to you that the electron absorbs it and that energy is taken on as heat in the metal. The electron, it gets tricky, but I would say to you the electron doesn't really gain the energy. The whole atom ends up gaining the energy by moving faster. But we'll learn later that the electron has certain rules as to how much energy it's allowed to have. And that's where we'll really get into what really happens. Over here, this is greater than the work function, so the photoelectric effect occurs. It happens. The fifth example is basically covered by the two examples you did in preparation for today's class. So we don't need to do that. What I would like to do is look at the examples here. And I don't want to spend a lot of time with this. As I was walking around the room, I was looking at those of you, at the work for those of you that had this out, and it looked like you knew what you were doing. If you want to find the kinetic energy of the electrons, then you need to say to yourself that we need to take the energy of the photon and subtract the work function. And I think you can tell that I'm a big fan of working in electron volts. To me, the energy of the photon will be the easiest thing to calculate. And I'm not going to worry about units here. This will be the energy of the photon in electron volts. And I'm not saying you have to do this in one shot. You might even decide to calculate each of these pieces separately. The work function in electron volts would be Planck's constant in eV seconds multiplied by the frequency and I'm going to actually show you, hopefully you've already done this. How many of you worked in joules? Okay, so I would just say to you that you should understand what it is I'm doing if you worked in joules, but you get the right answer anyway. Okay, so 1242 divided by the 450 is 2.76 eV. Planck's constant multiplied by the frequency is 1.449 eV. You've already got most of this written down if you've done the question. I'm not going to write it down. So if we take 2.76 and subtract 1.449, we get 1.31 eV. So that's the kinetic energy. Now, and that's the answer to A. If you wanted to find the kinetic energy in joules, you could have done what I think many of you did, or you could have done what I did and then multiply by the conversion factor of 1.6 times 10 to the negative 19 joules per electron volt. Okay? Of course, this is necessary, so that's the answer to A in joules. This is necessary for B. Because B, so we've already answered A. Right? Whoops. We have already answered A. But for B, you have to use EK equals 1/2 mv squared. And that formula only works in joules. So you need to take now this energy, and I am not going to write anything down here. You should be able to figure out if this is the kinetic energy of the electron, what the speed is, because probably 3 or 4 dozen times we've done a very similar calculation. Multiply the energy by 2, divide by the mass, and it is an electron, and take the square root. So we get the answer to B, 6.79 times 10 to the 5 meters per second. Any questions with A or B? Okay. Now you get to C, and C asks you for the stopping voltage. Well, you have to use this formula, EK equals QV stop. I'm curious on your formula sheet. Can you remind me, does it say EK max? It does say EK max. Again, I don't think it's that big of a deal. We use the word max there to indicate under ideal situations, this is the maximum possible energy that the electron could get. But this also has to be in joules. So let's say you calculated, I'm going to go back here and do the 1.311 EV. Let's say that what you did was you calculated the answer to A in electron volts, and it's sitting there on your calculator. And then you say, I want to find the stopping voltage. So this is an energy in electron volts. If you want to calculate the stopping voltage with this formula, you need to convert that number to joules. You with me? And converting electron volts to joules involves multiplying that by 1.6 times 10 to the negative 19. This is not coulombs, this is joules per electron volt. And I get this number, which is the kinetic energy in joules, and this number is now going to go here, and you're going to solve for the stopping voltage. What are you going to have to do with the energy in joules in that formula to get the stopping voltage? Well, you'll have to divide by the charge of an electron. So I go back to my calculator, and I take this number and I divide by 1.6 times 10 to the negative 19. This time I'm dividing by coulombs. I mean, I hope everybody sees what's going to happen. We started off with 1.311. We multiplied by that number to change it to joules, and then we're going to divide by the same number to get it into volts, which totally makes sense. If the kinetic energy of an electron is 1.311 electron volts, then the stopping voltage is 1.311 volts. I will, everybody, never use this formula. I just don't use this formula. If I ever want to find the stopping voltage, I just find the kinetic energy in electron volts, and that's my answer. If I know the stopping voltage, let's say I'm told the stopping voltage is 2 volts, well, then the kinetic energy is 2 electron volts. And if I want to work in joules, I just convert 2 electron volts to joules. All right, let's take a look at the next one. This time you were given electrons that are ejected from the surface, and the work function is 3 eV. How many of you found this one a little more challenging, like thought-provoking in terms of trying to figure out what to do? I think that's normal. When you say the kinetic energy that the electron has outside of the metal is the photon energy minus the work function. That makes sense. But if you start to do the opposite, you discover that the photon energy has to be equal to the kinetic energy of the electron plus the work function. This is really the law of conservation of energy. This is the initial energy. This is the final energy. Before the photon's absorbed, it has energy. Afterwards, where is the energy? The electron has some as kinetic. And here's where it gets tough to think about. The rest of the energy is stored in the atom somehow. It's stored as potential energy. So if you want to know the energy of a photon of light, you're going to have to find the kinetic energy of the electron from this, which is pretty easy. You're going to have to add that to the work function, which you're actually given, and that will be the energy the photon has. You have to grapple with the fact, though, that when you calculate the kinetic energy of the electron, it will be in joules, and the work function is given in eV. So how do you reconcile that? How do you fix that problem? Well, you could do this. You could calculate the kinetic energy of the electron. This, of course, is in joules. Then you could convert it to EV and add 3 to it. Or we could convert the 3 EV to joules and add that to this number on the calculator. I'm going to divide this by 1.6 times 10 to the negative 19 joules per EV to get 3.96 EV. That's the kinetic energy of the electron. And think of it this way. That's how much energy the electron got to keep. So it must have been given more than that if it was allowed to keep 4 EV and there was a cost of freedom of 3 EV, it must have been given 7 EV. That's maybe a kind of a common sense viewpoint here of why you're going to have to add these two numbers together. Anyway, you get 7 EV. What's the frequency of the incident light? Well, that's 7 EV, or I'm going to put 6.96 EV, is equal to HF. Not HF0, HF. Because that's the photon energy, so it's the photon frequency. If you worked in joules, then you would have a different number here, but you would be dividing by a different version of Planck's constant. So if I divide that, I still have to add that 3 on my calculator. If I divide this photon energy by Planck's constant in EV seconds, I get 1.68 times 10 to the 15 hertz, which is the answer to the second part of this question. So the frequency you get here, is the answer to this question. If, on the other hand, you take 3.0 EV and set it equal to HF0, because the work function equals Planck's constant times the threshold frequency, then that frequency that you get will be the answer to this question. There are other ways you could have done this question. But just to finish this off, if I take 3 divided by 4.14 multiplied by 10 to the negative 15 hertz, EV seconds rather, I get 7.2 times 10 to the 14 hertz. So I know I said that we would use most of today's class, almost all of it, for you to practice, but I felt that that extra little handout I gave you here might just get you thinking a little bit more about everything that's going on. And, just to let you know, next time I do this unit, I would definitely redesign it. I'd just put those examples in here. Anyway, I think I've got page 47 here. Is that right? Okay, so page 47, there's a whole whack of problems dealing with the photoelectric effect. I think there are 18 of them. My philosophy has changed. It's not homework, it's practice. You practice at this level what you feel you need to practice to get really good at it, or as good as you want to get at it.